this session of this video, we are going to talk about mechanics. We all know that mechanics is a broad topic in physics, and we need to start with the basics one. And one of the basic subtopics in mechanics is dimensional analysis. It's very important to know the importance of dimensional analysis in mechanics. And now, so with that being said, dimensions simply denote the physical nature of a quantity, which means the distance between 2 points can be measured in feet and meters. And these are the different ways of expressing this distance in a length form. And in mechanics, it's conventional to use the quantities of length, mass, and time, which are here. They are very important to use these physical quantities. Is very common in mechanics. Therefore, if any other physical quantity is given to you, like force, velocity, distance, you have to express them in length, mass, or time. One of the things that you have to also take note is we have this symbol here, and this symbol here is dimension of physical quantity. So instead of you to write the dimension of a velocity, you just write it the dimension. We're using the symbol here. The dimension of velocity is equal to that and that. That is the purpose for this symbol. Now, another thing that I would like to talk about here is trig function appearing in equation is dimensional. So anytime you have any trig functions in in equation, for example, when you have a sine of maybe 2 pi ft here, now this one here is dimensionless. It doesn't make sense in mechanics. That's what I have to say about that. And now another example that I want you to pay attention to is, I have an example here. So here I wrote x, the dimension of x is equal to L, which is equal to L times C over T, which also can be equal to L over T times T, which can be also equal to the velocity of the dimension of velocity times the dimension of time, which can be equal to the dimension of acceleration times the dimension of time squared. Now, with this kind of equation, or the example which I have provided here, it appears that the x here is equal to at squared, which is not correct. However, or which is not correct, let me say it's like that. So what they are trying to say that the equation here relate to the distance traveled by the acceleration and time. However, the equation is not even correct in this case of constant acceleration starting from rest. So the reasonable or the correct form to use for this kind of statement, it should be x should be equal to half times acceleration time squared. That should be the correct one. What am I trying to say here? What I'm trying to put here, or the point I'm trying to make here, is there's a limitation in using dimensional analysis to discover relationship between physical quantities. Now, what is the importance of dimensional analysis in mechanics as far as physics is concerned? One of the importance of dimensional analysis is we use dimensional analysis to compare two equations, or to verify if an equation is dimensionally correct. Another important of dimensional analysis is we can derive equation using dimensional analysis. And in this video, we are just gonna take how to use dimensional analysis to verify if an equation given is dimensionally correct. In our next video, we will talk about how to use dimensional analysis to derive equation. So without wasting much time, let's see our first example here, which I've already solved, but I'll explain it to you here. So first example says that we should show that the expression, the v here, which is velocity, is equal to the initial velocity, which is v naught plus a t. The a here is acceleration, the t here is time, is dimensionally correct. So the strategy of solving this kind of question is, first of all, you have to analyze each term here. You have to analyze each term. So you analyze each term. Then when you are done, you then find each term that you have analyzed, you find their dimension, find their dimensions. Then when you are done with that, the last thing that you have to do is to check to see if all the terms agree with each other. That is that's the valid you check it is valid, like on both sides. So in this kind of question, we will first analyze v here. So v here should be equal to the v naught. They are all velocities, so they will have the same dimension. Therefore, the unit of velocity is meter per second. So where we said meter, we use meter, we use length to represent meters or distances. So m here, we represent m here with L here, then second with time here, which is capital T here. So the dimension of v is equal to the dimension of v naught, equal to L over T here, right? Now let's come to the other side. We have the dimension of acceleration times the dimension of time together. Now, what is the dimension of acceleration here? The dimension of acceleration here is L over T squared times T, right? So the T here is for this time here, and the acceleration here, this is the dimension for it. Now, okay, so the dimension of A, which is acceleration, L over T squared, equal to, you can also write it in this form, L T minus 2 times T. Then here you use a algebraic expression or a algebraic way of solving to solve this kind of thing. So we have here LT minus 2 plus 1. Then we have LT minus 1 here. So when you combine them all together, the dimension of acceleration times the dimension of time, you're gonna get this like this. Then when you are done, you check if it is valid or it is correct. So we compare. So we saw that the dimension of velocity here and the dimension of acceleration times time is the same thing. Therefore, the expression v equal to v naught plus at is dimensionally correct. Let's go to our next example. Now, our next example, you can pause this video and try to see if you can solve this question. Now, in this video, we have the period of a simple pendulum defined as the time necessary for one complete oscillation is measured in time units, and it is given by t, which is the period, equal to 2 pi times the square root of L over G. The L here is length and the G there, so L here is length, and here's the gravitational force here, right? So you first analyze each term. So we'll take t here, so the dimension of t. Now whenever you are given a question, this is how you're going to solve it step by step. Make sure you use the dimension symbol here. It's very, very important. If you don't bring it, all that you've done is wrong. So the dimension of t here is equal to 2 pi times square root of the dimension of L over the dimension of the gravitational force here. You already have the dimension of L here, which is the length, which is L, capital L here. So the dimension of G here is what we are going to get here as L over T squared. We will come and just put it here, and we will get the dimension which is here, T is equal to 2 pi times the square root of L over LT minus 2 here. Then we just square both sides so that we can verify it. Now, when we square both sides, we are going to get the dimension of t squared is equal to the 4 pi squared L over LT minus 2. You can also write it in the form of the dimension of t squared is equal to 4 pi squared L here times L minus 1 times T2. So in using algebraic expression, we can just cancel this one out. L can cancel L here because here is plus 1 and here is minus 1. When they add them together, it is 0. We will just cancel each out. So therefore, we are going to have the dimension of t squared is equal to 4 pi squared t squared. Now, with this form of equation, the 4 pi squared here is dimensionless or is constant, so we don't even count it. So when you're comparing the equations, do not add the 4 pi squared. It is dimensionless, so we don't add it at all. So here we are gonna have t squared is equal to t squared, which is dimensionally correct. Let's see our next example. Now, in our next example, we have gravitational force is equal to force times r squared over m1 times m2. We are going to show if it is dimensionally correct. That's what we are going to do here. Now, we know that first of all, we have to analyze first each time. So the dimension of gravitational force is m minus 1 t3, then L3 times T exponent negative 2 here. So this is the dimension of gravitational force. Let's go to the other side of the equation, which is the F, which is force radius squared over mass 1 mass 2 here. Let's analyze each term here. So we'll come to force. Let's take force. So force here is equal to acceleration times mass, right? So the dimension of force is equal to LT minus 2 times m here. So the dimension of F is m LT squared. Let's put it here. This equation 1. Now let's come to the r squared, which is the radius. So r here is radius, right? And r is in distance, which is length. So r is measured in length, which is L here, right? So therefore, we have the dimension of r squared here to be L squared, right? We'll also put it here 2. Now let's come to the m1, m2. m1 is equal to m2, which is the mass, put in m here. Therefore, the dimension of m1 is equal to the dimension of m2, should be equal to capital M here. This is 3. We put all the equations together and see what we are going to get. So let's put F first, which is the force. So we have m LT minus 2 here, which is the exponent minus 2 for the t, times L squared for the radius, all over m1 m2, which is m here, right? Which is m here. So there's this mistake here that we need to correct. Here, yep, there we go. They're gonna have this, then we'll have that here as well. So let's take this one aside here, right? So that one is there. So therefore this I'll find out this one. So here we're gonna get L 1 plus 2t minus this over m that. Then we have L3 t exponent negative 2, then m exponent negative 1. So this is it. So if you compare both sides of that, you can see the dimension of here, which is the gravitational force, m minus m exponent negative 1, L exponent 3, t exponent 2 is equal to the dimension of fr squared, then m1 m2 here, which is L3 t minus 2, then m minus 1. It is the same. So this is dimensionally correct. Right. So this is the end of this video. In our next video, we are going to use dimension analysis to derive equation. And if you have not subscribed to this channel, I will encourage you to subscribe to this channel, like this video, and also share it to your colleague. Thank you for watching this video, and I'll see you in the next video. Bye.